All right, this is motion 2.2 velocity. This is a rather large chunk of the content for physics. So I'm going to break this down step by step, but I highly encourage you to go through the various activities, hands-on labs, videos, practice worksheets, and all that good stuff on Schoology. 2.2 says to explain velocity as A, a vector quantity that represents the rate at which a position changes. B, it can be calculated by dividing displacement, or the change in position, by the elapsed time. C, it may be positive or negative depending upon the direction of motion is not always equal to speed. Provide examples of when the average speed is not the same as the average velocity. D, objects that move with constant velocity have the same displacement for each successive time interval. E, while speeding up or slowing down and or changing direction, the velocity of an object changes continuously from instant to instant. And F, the speed of an object at any instant or a clock reading is called instantaneous speed. An object may not travel at this instantaneous speed for any period of time to cover any distance with that particular speed, especially if the speed is continually changing. So let's go through this one at a time. And I have a little trusty helper here today, Mr. Buggy. The first one says that velocity is a vector quantity that represents the rate at which a position changes. So we know that velocity is a vector quantity. And let's review this really quick just so that we remember that a vector quantity or a vector is just like a fancy term for an arrow. So that means that it has to include a direction. So we know up front already that velocity is a vector quantity, and it says that velocity is the rate at which an object's position changes. So if we're talking about an object's position changing, that means that it is moving, changing direction. It could be doing various things, but its position is changing, and you're determining the rate at which that is happening. Now, to calculate velocity, part B, it says that you would calculate velocity by dividing displacement over the elapsed time. All right, well, if you guys recall, when we talked about the objective before this, 1.2, we talked a lot about displacement. Displacement is also a vector quantity, just like velocity. So that's where you get your direction. Whatever the direction of the displacement is going to be the direction of the velocity. And then you just simply divide that by the elapsed time. So you first have to calculate, okay, well, where was the initial position of the object? Where was the final position of the object? And exactly how much time did it take? So you will oftentimes see velocity as displacement divided by time, or you might see it as something called change in position. This is a little delta symbol, and it's for change in. It's a fancy math symbol, and X is symbolized for position. So displacement is a change in position. Velocity is that change in position divided by the elapsed time. So that's where you get the definition of velocity, the rate at which the object's position changes. How much time did it take for its position to change? Now, part C says it may be positive or negative depending on the direction of the motion is not always equal to the speed. So this is a really interesting one. If you recall before, we talked about some scenarios where let's say the distance and the displacement of the object, starting position here, running the 400 meters around the track, and ending here, which happens to be the exact same position. Do you remember when we said, well, the distance is 400 meters around the track, but the displacement was 0? Because this was the starting position or the initial position. This was also the final position. So that means that the distance is 400 meters. The displacement, it's going to do display because I'm being lazy, is 0 meters. Well, what if it took us, 10 minutes? We're running rather slowly here around our 400 meter lap track. Well, if that takes me 10 minutes to get around the track, the distance, if I'm calculating just the speed of the object, because we're looking at changes or differences between speed and velocity. Well, if I want to calculate the speed of this particular object running around the track, perhaps it's you or a slow sibling or something like that, we have to take the distance, which is 400 meters, and divide by the elapsed time, which we said was 10 minutes. Okay, well, 400 meters divided by 10 minutes is just going to give me 40 meters per minute. That's my average speed around this particular track. Well, my velocity is going to be my displacement, or change in position, divided by elapsed time. Well, my velocity was 0 meters. My time was still 10 minutes. So guess what? I have 0 meters per minute velocity. So I have no average velocity because I have no displacement. My displacement or my position did not change, therefore I cannot have a velocity. So even though the same person is running around the track, when we go to say, well, what's their speed? 40 meters per minute. What's their velocity? 0 meters per minute. Those numbers are vastly different. Now, let me highlight this because this is a huge error in physics. A lot of people say, oh, well, if velocity is just a vector quantity that represents the rate at which a position changes, that's kind of like speed, except it has a direction because it's a vector quantity. That is wrong. Velocity is not just speed with a direction, because if that were true, the speed would be 40 meters per minute. The velocity should also be 40 meters per minute with an assigned direction, and that is absolutely not true. There are situations, though, where that is true. Again, when we talked about the difference between distance and displacement, remember when I gave you an example of maybe traveling in a straight line? So I'm going to go from A to B. I'm going to go from the negative side to the positive side. Okay. Well, here is my distance that I traveled, every step I took from A to B. Well, that also happens to be my displacement as well, from A to B. So let's say this is, make our numbers easy here, 50 meters that I traveled, and it took me 5 minutes to do it. Well, if I travel 50 meters in 5 minutes, my speed is just the total distance traveled, 50 meters. So my speed is 50 meters divided by 5 minutes. So my speed there is 5 meters. Oh, wow. I can't do math, you guys. Apologize. 10 meters per minute. That's my average speed for this particular example. Well, my velocity is 50 meters. And I'm going 50 meters in the positive direction over 5 minutes. So my velocity is positive 10 meters per minute. So in this particular example, the velocity is the speed, the exact same speed attached with a direction or in the positive direction. But that is only when the distance and the displacement are the same. So please, please, please make sure that you're not making that error, because I will tell you a lot of the resources online honestly say that. They're like, oh, it's easy. Velocity is just speed with a direction. Well, you know that that's not true in every situation. The next example talks about objects that move with constant velocity have the same displacement for each successive time interval. So this is where my lovely assistant Buggy comes in. So if I've got my Buggy here, I'm going to turn him on. He's a bit slow, but that'll be beneficial to me here. Okay, so there's my Buggy, right? If I were to track the progress of my Buggy, maybe some of you did in the intro lab for the Buggy lab, maybe I drop a dot every second as my Buggy goes by, okay? So he's going pretty slowly. So I've got a little metronome going in the background. I don't think you guys can hear it. And I'm going to drop a dot every second. Here we go. Okay. Check this out. My dots here might be a little bit hard to see. I'll make them a little bit bigger for you. My dots here are perfectly spaced. Same amount of space between every dot. So what does that mean? It says that objects that move with constant velocity have the same displacement for each successive time interval. Well, let's just make up a number here. I'm not going to actually measure it out, but let's say here are the little vectors for my buggy moving. Indicate the direction that he's going. Well, my displacement, we'll call that, I don't know, we'll call that 15 centimeters. Also 15 centimeters. Also 15 centimeters. Also 15 centimeters. Well, I dropped a dot every second, right? So that took 1 second. 1 second. 1 second. 1 second. That's an example of constant velocity. If it's constant, it's going to have this same displacement. I guess I need to indicate a direction, so I'm actually talking about displacement. So we'll make this negative side. We'll make this positive side. So negative 15 centimeters, negative 15 centimeters, negative 15 centimeters, negative 15 centimeters. So what that means is for every 1 second or every time interval or successive time interval each second as I go, the displacement of my buggy was negative 15 centimeters. Negative 15 centimeters, negative 15 centimeters. So it traveled the same change in position or had the same change in position every second. And that's what they mean by having constant velocity or the same displacement for each successive time interval. The next little part of that objective kind of ties in. It says, well, while speeding up or slowing down and or changing direction, that's an interesting one, and or changing direction, the velocity of an object changes continuously from instant to instant. So if I'm talking non-constant velocity, so constant velocity is when the displacement changes the same for each successive time interval versus non-constant velocity. That means that the interval, the successive time interval, the displacement changes every single instant. It could speed up, it could slow down, or it could change direction. That would be considered non-constant velocity. Well, spoiler alert, guess what non-constant velocity is? Acceleration, which is going to be the next part of your objective. The last piece of the puzzle here talks about something called instantaneous. So they talk about the term instantaneous. And the last part of the objective reads, the speed of an object at any instant or a clock reading is called instantaneous speed. An object may not travel at this instantaneous speed for any period of time or cover the distance with that particular speed, especially if the speed is continuously changing. So what they're trying to say here is you do need to understand what the difference is between instantaneous speed. So I'm driving in my car, okay, and I know that you guys don't drive cars, so I'm gonna get in the buggy. So I'm in my buggy and I'm driving along, and here I am. I'm checking out my steering wheel. It needs to focus on my little steering wheel here. And when I'm driving my car, there's a little indicator on my car as I'm driving called a speedometer. And I know that you guys have seen this in probably your parents' cars. Sometimes you see like a big crazy circle and it has 0 miles per hour. Miles per hour, and then it goes up to 10 miles per hour, 20 miles per hour, 30, 40, 50, 60, 70, 80, and if you're really lucky it goes up past 100 miles per hour, and you're going like super fast. So there's something called a speedometer, and in most cars they have a digital speedometer, and it just spits out the actual speed of the car, and it just puts it on a reading. Well, if I've got my little speedometer here and I'm driving, instantaneous speed is kind of like me driving in my buggy and just glancing down at my speedometer at any given second, at any instant, literally a snapshot of time. So say my speedometer is reading right here. That means at that particular instant, I'm going 45 miles per hour. That would be considered at that very moment my instantaneous speed. Now, I could travel 45 miles per hour at a continuous speed and reach a constant velocity, but the objective is saying that you don't always have to go this 45 miles per hour. In fact, as say I'm speeding up, my 45 miles per hour is going to change to 46, 47, 48, and so on, or as I'm slowing down, 44, 43, 42, so on. So my instantaneous speed may continuously change, and I may not achieve that instantaneous speed again, but instantaneous speed, sorry, little interruption over the intercom here. My instantaneous speed is going to be very different at that instant than, say, my average speed over a period of time. So let's talk average speed just real briefly so this makes a little bit more sense. When I drive to school, you know, I back out of my, or I'm parked in my garage and I'm going 0 miles per hour. Well, then I speed up and I go, say, 20 miles per hour through my neighborhood. And then I speed up even more on the highway, you know, maybe, I don't know, down here near 100 miles per hour because I'm a speed demon. And then I have to slow down when I get onto other roads. I speed up again. I have to stop for stoplights, whatever. If I find my average speed of my trip, well, maybe the average speed from home to school is like 37 miles per hour. That's just my average over the whole trip. Well, at any given moment, if I glance at my speedometer, that's my instantaneous speed. That is not necessarily the same as my average speed. So, I know that was a lot, and I'm sorry that this video is excessively long. I just want to thank Buggy for assisting me today. That was very helpful. Please do check out the activities on Schoology. Sign up on the help board. Let me know if you have questions, and then you can move on to acceleration.